So number 5 then, from the 2017 Mathematics of Mechanics, 4 marks again. Here, a little bit of light relief from the mechanics of it then. Express this rational expression as a sum of partial fractions. Well, the numerator's already of a degree less than the denominator, so we've got a cube in the denominator, which means you can express it straight away then as the sum of 2 fractions with these denominators. X minus 3, which is linear, so the top would have to be a degree less, that's a constant. The irreducible quadratic, x squared plus 5, so the numerator would have to be a degree less, so that will be a linear expression, bx plus c. Now, doing that gets a mark. Now, the way this is meant to work is these 2 expressions are meant to be identical. So if you were to render that back into a single fraction like this, the 2 parts should be the same. So putting that back would be multiplying a by this denominator and bx plus c by this denominator, because the new denominator would have to be the product of those 2. Well, you'd probably say just take that across and multiply that, but it's the same effect as multiplied by these. So a gets multiplied by x squared plus 5, and the bx plus c gets multiplied by x minus 3. Now, that would be the numerator on this side. The denominators would be the same on both sides, and if the fractions are the same, the 2 numerators are the same. So you can just equate the numerators. This numerator should equal that numerator. So you get this equation for a mark. I say equation, it's more than that, it's an identity. It's true for all values of x, all relevant values of x. Mathematically, the way to do that would be to multiply this out until it had the 3 terms in it, x squared, x constant, and equate them term by term. But since it is an identity, it means it's true for all values of x, so you can put in any values you like that are valid. Now there is a wee thing here. This original expression has got this denominator. That's not valid when x is equal to 3. But you tend to put that back into the cupboard when you come to this part here and not speak of it again. So if you're doing it by putting values into both sides, then the obvious value to choose, just looking at this on its own and forgetting about that, would be choose x equal 3. You'd call that a knockout value because it knocks out this term. You don't worry about its heritage. Well, if x equals 3, that term gets knocked out. That becomes 9 and 5 is 14, so it's 14a. This side becomes, there's lots of bits here, 3 9s are 27, 4 3s are 12, plus the 17. So that comes to 56. So if 14a is 56, that means a is, and that goes in exactly 4 times, that means a is 4. Now, after that, using that knockout value with no shame, I'm going to go back to the original sort of mathematical way of doing it, which is to equate corresponding terms. Then there's no problem about where numbers come from. So I'll say now for the next part, rather than put in some other numbers and get simultaneous equations, the x squared terms on both sides must be the same. On this side, the x squared terms are ax squared and bx squared, so you can't do it. So that means I've got a plus b lots of x squared on this side. This side has got 3, so straight away I get b. b will be 3 minus the a, so b is negative 1. Similarly, if I go for the constant term on both sides, I've got 5a. b can't produce it because it's stuck with an x, minus 3c should give the answer 17. Which means that 3c, taking it over, reading it this way, will be 5a's, which are 20, minus the 17, that's 3, divide by 3, c is 1. The way the marks went were, you got 1 mark for the first 2 of the constants, the other mark was for the remaining constant, and just putting it all back together. So what was that equal to? Well, a was 4, so that's 4 over x minus 3. Now, b's negative 1. So you could write minus, but then I have to make the other one negative, so it ends up as plus. So I think here I'll just do plus. And instead of having negative x plus 1, I'll put 1 minus x. And that's the last mark.